First, I'm going to distinguish between the exchange statistics versus exclusion statistics. Namely, physically, there are two different meanings about statistics. Then I'm going to talk about the general formulation of exclusion statistics. Then I will talk about the realization of some seemingly ad hoc postulates about exclusion statistics, okay? Namely, they can be realized in one-dimensional exactly solvable many-body models. Then these new exclusion statistics can also be exactly realized in fractional quantum Hall system, which was a very hot topic nearly 30 years ago. I'm going to talk about computer tests of the theory. In recent years, these new exotic statistics are found to be realizable in 2D exactly solvable many-body models, especially those for topological matters. Finally, it's summary and discussions. Okay, introduction, only one page. What's the difference between the exchange statistics and the let me try to shift, okay. Okay, exchange statistics means when we want to exchange two identical particles, we look for the a phase change in the many-body wave function. Okay. Usually we have fermions and bosons. For bosons, the actual phase is 1. For fermions, when we exchange the two particles, the wave function change by sign. So when we write the sign as EI theta, theta must equal to pi for fermions. However, theoretically, it's allowed to have an arbitrary phase, EI theta, which theta is between 0 and 2 pi. When theta is not equal to 0 or pi is called Anion. From the braid group theory of mind, it can be shown that this kind of exchanges statistics or anions can be realized in two spatial dimensional systems. Therefore, for many-body wave function, if we use complex coordinates to denote the coordinates of the particles on a plane or on a two-dimensional surface, the wave function actually must be multi-valued when theta is not equal to 0 or pi for anyons. So in general, the wave function is the following form: a gestural type prefactor, which is a product zi minus zj for any pair of particle indices I and j raised to power theta over phi times a symmetric polynomial of the complex coordinates. Physically, according to Wilczek, the anion can be viewed as a composite of a charge and a flux field. Okay, so when we try to exchange the two anions, the charge in one anion can see the flux in another anion. This is a well-known Arnold bomb effect. Okay, so this is exchange statistics. We just look for exchange phase for the many-body wave function. In quantum mechanics, especially in quantum statistics mechanics, we will have the so-called exclusion statistics. Exclusion statistics is just to consider the so-called statistical weight W for the many-body system. W, we know that in well-known Boltzmann factor, the entropy is equal to Boltzmann constant times log of W. Then W is the so-called statistical weight. And when we have capital N of identical particles, the weight, statistical weight is given by combinatoric factor. So here we have G equal to one particle states. When alpha equal to 0, we get the Bose weight for bosons. For alpha equal to 1, we will get the statistical weight for fermions. The point is that, the principle of physics actually allows us to have an extra term on the top column. Namely, we can parameterize the second term by an real number alpha, and we call it 1 minus alpha. Okay, then you can see that alpha equal to 1 corresponds to fermion, alpha equal to 0 corresponds to boson. The point here is that, alpha can be arbitrary positive number, real number, okay, between 0 and 1. So in that case, we have new exclusion statistics. Using the statistical weight is my way. Originally, this was proposed by Jordan in year 1991. His way is a bit different. Later, I will explain it, okay? Namely, we may consider boson, then we take alpha equal to yeah, so the first term G plus alpha times 1 minus 1, we call the available single particle states when we add the nth particle into the system with n minus 1 particles haven't been present in the system. Okay, so then this G effective is the available single particle states when we add the nth particle. Okay, so then explaining this way, we can, if we change the particle number n, then we can see the change in the so-called G effective boson actually changes by the second term, the n in second term. So this change actually, because the second term is linear in n, so we will have a linear relation between delta G effective and delta Nj, and the constant coefficient Gij is called the mutual statistics. Namely, the presence of some particles actually will make the decrease in the available single particle states for particles later get into the system. So this is why we call it as exclusion statistics. Namely, when we put particles one by one into the system, then the available single particle states for new coming particles will decrease. Okay, so all right, how to get, okay, let me try then. So as I've mentioned, the Jordan's formulation is a bit different, but yeah. However, I use the statistical weight, okay? So for boson, it's this one, G plus n minus 1 choose n. For fermions, G choose n. So for generalized exclusion principle, we introduce a statistical parameter alpha here. Then I can introduce available single particle states for the nth particle. Okay, so it's given by these expressions. So in the usual bosons or fermions, this G effective is independent of n. However, when alpha is not equal to 0 and 1, we have the linear independence of G effective on n. Then the, okay, for more than one species, actually, we introduce the species index I, and the ansatz for the statistical weight is the product of the I's WI for the I species. Then we have the product over all species. Then again, we may consider Okay. We may consider the G effective. Why? Okay. Then the G effective actually becomes NJ dependence. It depends on the particle numbers of all possible species. Then the coefficient of ij is called the statistics matrix. When I equal to j, we have the diagonal elements. I not equal to j, we call it the mutual exclusion statistics. We notice that the above assumption is independent of spatial dimensions. It's not restricted to be in 2 dimensions. Also, we allow mutual statistics, namely the presence of the J's particle may affect or decrease the available single particle number of available single particle states for the ith species. Okay. However, we can easily go back to the usual fermion and bosons. Okay. Then to consider the quantum statistical mechanics, we can introduce the idea of the generalized ideal gas, namely the total energy of the system is the sum of single particle energies, and the statistical weight is product of the all species. Okay, statistical weight for all species. I have to emphasize that depending on the system, the meaning of the species is a little bit different from the usual species, namely particles with different energies or other quantum numbers may be viewed as different species. Okay. Yeah. Then we can consider grand canonical ensemble. Okay, so the partition function is of this form. Then when we apply the maximum entropy principle, we can get the so-called most probable distribution. So the ratio Ni bar divided by Gi bar, okay, we call it the most probable distribution. Then the this distribution satisfy this equation, and this Wi's satisfy an equation like this. Also, it satisfy this equation. Okay, Wi actually, yeah, is just exponential of epsilon I divided by kBt. Okay, so then Wi as a function of yeah. So from this set of these two set of equations, we can solve Wi as exponential function of these exponentials.
Yeah.
So these are the generalized ideal gas, okay? And assumption of capital W, the generalized one, is this one, okay? Is this one. Can you see?
Yes, thank you.
My postulate, okay, yeah.
Yeah.
So, yeah, these two equations are important to obtain the most probable occupation number distribution. So for the single particle cases for bosons and anyons, bosons and fermions, we will get the usual Bose-Einstein distribution and the Fermi-Dirac distribution. And the consistency is that we use these distributions to compute the variance of the occupation numbers. We can show that, yeah, the variance actually tends to 0 when the occupation number, most probable occupation number becomes very big. Okay, so yeah, the above answers looks like ad hoc, but however, I can show that it actually realized in the familiar models. So first is one-dimensional integral many-body models. Beta ansatz soluble or Sutherland long-range interaction model. So we assume there's no internal degree freedom. So we have one species, okay. So this is a many-body Hamiltonian with pair interactions potential. Then the integrability of the system tell us that, yeah, two-body phase shift during the two-body inelastic speckling actually determines everything. Total energy is the sum of the usual kinetic energy momentum in one dimension is also the sum. Then the beta ansatz equation for many-body system finally gives us thermodynamics. This was shown actually in late 60s by C.P. Yang and C.N. Yang. C.N. Yang and his younger brother. Then the beta ansatz equation gives us this formula for counting of states. Here, the theta of KMS Kj is two-body phase shift. And the first term is the choice of some integers, okay. So this equation is the result of periodic boundary conditions plus the Yang-Baxter equations. Okay, so we can take the particle number n tends to infinity and the length of the circle or the system tends to infinity with n over L fixed. Then we can get an integral equation. Okay, yeah. So this sum becomes an integral with rho of k is the momentum distribution. Okay, so Yang and Yang get an integral equation like this for the distribution of momentum or pseudo momentum. However, the last term is an integral over k prime, and we have the derivative of theta k minus k of the phase shift. Okay, actually, according to our counting rule, the mutual statistics in this model, okay, takes the following form. The first term is a delta function, then the second term contains a derivative of, So this agree with our postulate. Okay, so we can determine the mutual exclusion statistic function like this. Okay, so if we write W of k like this, then the equation for Wi obtained actually becomes to this integral equation. This is the result of okay, so then we can see one-to-one correspondence of the between the Yang and the Yang's result and the discrete formulation I have given before. So two special examples are when the pair interaction is a delta function with positive coefficient. So we have repulsive interacting boson delta function interaction. Okay, so theta of k phase shift can be solved to get this one theta of k. Then the mutual statistical function actually is given by this delta of k minus k prime minus pi over 1 times this function. It can be shown that when theta tends to 0, we have only a delta function. When c tends to infinity, then we get another we get the second term to be 0, then we get the delta function. Similarly, we can consider the so-called Collegero-Sutherland model for fermions, and the pair interaction between fermions is given by a Coulomb constant G divided by distance squared. In this case, from the following, from the above, we can get the statistical parameters or functions actually is constant lambda times delta k minus k prime. Okay, the lambda is determined from G, and this system has a duality between lambda and the inverse of lambda. At low temperature, this recurves back to the C=1 CFT for the system. Okay, so lambda is a statistical parameter for. Therefore, we can conclude the collateral-Sutherland model actually is a model for excitations being exclusion. And the exclusion statistical lambda is determined by the coupling constant in the long-range interaction term. Okay, so another explicit result for lambda exclusion is given by the distribution function. Okay, W is function of zeta. Zeta is given by this exponential. Okay, so W is a function of zeta, and this W satisfy the functional equation like this. Okay, one need to solve this functional equation to get the distribution function. However, it's easy to check that when lambda tends to 0, the W of zeta is equal to zeta minus 1. We get both statistics. When lambda equal to 1, W of zeta is equal to zeta, give us the fermions at low density. Actually, all distribution comes back to the Boltzmann distribution at very high temperature. And at the 0 temperature, actually the system has the Fermi or quasi-Fermi surface at 0 temperature, namely Ni is equal to 0 if the single particle energy is bigger than the Fermi energy, and equal to 1 over lambda if the energy is less than free energy. Okay. All right. So yeah. Also, we did a work using the exclusion statistics, and we use the bosonization trick to get the low temperature critical exponent. And we find that actually when temperature is close to the absolute 0, we can define the operators and recover the low energy behavior of the whole system to be the Lottinger liquid. Okay, so Lottinger liquid can be viewed as a fixed point for one-dimensional exclusion lambda, and Jordan's well-known result for Lottinger liquid actually can be completely recovered. Okay. It's a one-parameter family. The one parameter in Jordan's result is E2 minus phi. And in C2-1 conformal field theory, the one parameter is called the compactified radius. In our notation, is just exclusion mutual statistics. Okay, then we can show that actually our ansatz or state counting can be realized for fractional quantum Hall effect on a sphere. And we can use computer experiments to derive all relevant result. Okay, now I need to, so in this case, you know, the numerical computation is done on a two-dimensional sphere. We put a quantized monopole as the center of the sphere surface. Then we can consider the ground state, and the excited state would correspond to the quasi-holes or quasi-electrons. Okay, so I need to go back to new sharing. General formulation. Exactly a soluble model in one dimensions. We have finished that. Then we may consider the mutual exclusion statistic for quasi-electrons and quasi-holes in the quantum Hall effect. The state counting is obtained by exactly diagonalization for interacting electron system. Okay, in the fractional quantum Hall system, there's so-called a hierarchy scheme actually for quasi-holes and quasi-electrons. Okay, because of a fractional quantum Hall effect, we have completely filled lowest lambda level. When we increase the filling fractional, then the lowest lambda level is not completely filled. We may have quasi-holes, or we have overfilled lambda levels. So some electrons jump to the next lambda level. We get the so-called quasi-electron states. Okay, so there are constraints on these filling numbers from which we can derive the statistics parameter matrices. For fractional quantum Hall effect, the incompressible states or completely filled lambda levels are obtained when the number of electrons is m times the number of magnetic flux. Usually m should be odd number. Okay, in this case, the statistics matrix in the Holden scheme can be shown to be this, and minus is for quasi-Hall, plus is for quasi-electrons. So we can see that the mutual statistic is necessary for the fractional quantum Hall case. Another one is called the composite fermions. That's the so-called Jane scheme. A different different set of statistical parameters are obtained between quasi-Hall and quasi-electrons. You can see the difference. Okay, it's the existence of the mutual statistics.
Yong-Shi, I think.
All right. This scheme one is Holden. Yeah. Matrices. And the third one is the gene scheme, okay? Yeah. In gene case, you know, electrons are considered as composite fermions. And in Jordan's case, the electrons are considered as composite bosons, okay? At T equals 0, absolute 0, actually, they give the same results, okay? So here is the derivation of the Jen's result, okay? Here, yeah, I will not repeat. However, for Jordan scheme, we have such constraints. And for Jen's, we have different constraints because the physical definition of particle is different because of the different physical picture. Okay, so this is Jen's result. This is Jordan's result. So with these statistics, we are able to consider thermodynamic variables. For example, equation of states for quasi-electrons and quasi-holes mixed system. Okay, so this mixed anion gas, when it becomes incompressible, we will get the fractional quantum hole plateau. So then the many-body state is a hierarchy state. We can prove that, you know, the above counting number give us the result about when the hierarchy state or incompressibility or fractional quantum state appears, which agree with experiments. Especially, we can show that the incompressibility condition leads to the filling factor to be independent of temperature. Okay, because the thermodynamics.
I apologize if I interrupted you, but the next speaker should talk quite soon. So I'm regretful to ask you if you can reach conclusion and maybe send all this interesting calculation to the secretary and we can check. And
Right.
she will upload the PDFs.
Okay, let me come back to the PDF, okay? Yeah. So I have some numerical result to show the validity of these assumptions, which give rise to state counting from exactly diagonalization. Finally, I can talk about emerging the exotic exclusion statistics in the model of topological matter. The model we're talking about is the so-called Leavenworth model, okay, which is a two-dimensional trivalent graph, such as honeycomb lattice, and we put representations of some group algebra or quantum group algebra as a link. Okay, yeah. So for the so-called double Fibonacci model, we can calculate the exacting spectrum, and we can show that actually the statistical weight satisfy the form we have, namely a product of different species. And then we can determine the anions in this system is a topological quantum field theory. We need to introduce two species, pseudo species plus the anion species, so we can determine the mutual statistics for the 3 particle. Then finally, we get the most probable occupation number distribution is of following form. What's interesting is that we can see an irrational called the golden mean actually appears in the most probable occupation number distribution. Okay. Finally, there are some summaries. I would like to emphasize only 2 points. The first point is that this new counting rules for statistical weight can be realized in realistic or semi-realistic models. Okay, and the dimension of this model may be different. So consider the possible applications. I think especially when we have phase transitions in the cosmology, okay, whether this new exclusion statistics would appear is a very interesting question. Okay, then the second question is that once the topological materials can be realized in the laboratory, then the thermodynamic behavior of the topological phases, I think, may need the new ideas as the exotic exclusion statistics as a future direction. Thank you very much.